Okay, our final talk today. Another name I'm going to mess up.
Call me
Jacob.
And
Okay, from MIT, Jacob Shen, the Lumina Simulation and Puzzles of high-redshift galaxies in the Roman era. So take it away.
Yeah, the simulation you requested. Hi, I'm Jacob. I'm a postdoc at MIT, and today I want to give you an introduction of a simulation that we have been working on over the last few years and made an announcement just a few weeks ago. It's called Lumina. It's an extremely large volume radiation hydro simulation. I will talk about how we can use it to explore a few puzzles of the high-redshift galaxies in the Roman era. At the start, I want to show this image again, the history of our universe. And the central question that we understand about cosmology and galaxy formation is how these primordial density fluctuations see this through Big Bang evolving to the galaxy population that we're seeing nowadays. And to complete this story, we really need to go to the very early phase of galaxy formation, which was largely blocked in the past. Over the last few years, JWST has made great progress in pushing the redshift frontier. We're seeing so many fascinating objects now at the higher and higher redshift that are challenging the canonical galaxy formation theory. Well, in the next few years, what Roman would do is expand the sample size observed by JWST and revisit this business with better statistics. And in the meantime, provide additional constraints from the large-scale distribution of galaxies. And to pair with this enormous data, observationally, we need better theoretical models to make predictions. And one common way to do this is to take a volume of the universe, simulate that from the initial condition, and reproduce the galaxy population. And this would need some subgrid models of galaxy formation. And the illustrative simulation was the first of its kind. It's a large volume hydro simulation of galaxies. It has a box size of 100 comoving megaparsec. But by today's standard, it's too small. Here I compare it to the Roman footprint if I place the simulation volume at redshift 6. And obviously, it would be too small for upcoming Roman surveys. The Illustris project itself has a successor called the Illustris TNG, which is probably one of the most successful simulation campaign. It features a slightly upgraded galaxy formation model. It also has a variant box with 300 comoving megaparsec. But this box does not have good enough resolution to give converged galaxy property predictions to the smaller volumes. So it's still not that useful. But nowadays, with 8 years past, with better computing facility and better code, what we can do now is to take, roughly speaking, the resolution and the physics of this 100 comoving megaparsec box and scale it up by more than 100 times in volume. And that brings us to the Lumina simulation. We have already completed this simulation. It reached around redshift 3, which is around the end of the helium reionization. It has a box size of 500 comoving megaparsec. Different from the TNG suite, this is a simulation, this is a radiation hydrodynamic simulation, which means that we not only follows the evolution of galaxies in the universe, we also trace the radiation produced by these galaxies and accreting supermassive black holes and follow their interactions with the intergalactic medium. So reionization and galaxy formation are modeled at the same time in a self-consistent way. And you can see that these are images of the topology of hydrogen reionization and the helium reionization produced in the simulation. And in each pocket of these ionized bubbles, there are hundreds of thousands of galaxies resolved. And to achieve this balance between box size and resolution, it turns out that we have to run one of the largest hydrodynamic simulations that has ever been achieved in terms of particle count. This is a typical propaganda plot that compares the mass resolution and the simulation volume. So Lumina sits here. The better you're closer to the upper right corner, the better the simulation is. That we have a few competitors here, like Asteroid Millennium TNG with comparable particle number, but those are like pure hydrodynamic simulations without radial transfer, which would make it way more expensive if you push through the same redshift. This is our team. The data of the simulation will be shared at our website in the near future. At the moment, we accept collaborations through private connections. In the following, I'm going to skim through some early results from Lumina before I jump to the main topic that I want to talk about today. These are some plots that I take from the intro paper. What's shown on the right just show the huge dynamic range of the simulation, where you can start from the whole volume, pick a big ionized bubble centered around a massive quasar, and then you can do a really aggressive zoom in by more than 1,000 times in length scale to see the gas distribution around 4 galaxies that are resolved and modeled with a TNG model. And on large scale, the plot here shows the helium ionization history produced in the simulation. It starts around redshift 6 and ends around redshift 3, which are consistent with existing observational constraints. This is a movie that flies through this sub-volume that I picked out in the last image. Remember that what you're seeing here is just only 0.1% of the whole simulation volume. This is a companion paper of the intro paper led by Aaron Smith, which studied the CMB optical depths, and probably not surprisingly that we get results that are fully consistent with what Planck measured. This is another companion paper led by me, which we study the AGN demographics in Lumina. We take the supermassive black holes in the simulations and pair that with an observationally motivated empirical model that split them into little red dot phase and normal AGN phase. And this can essentially reproduce all the population level observations of high redshift AGN now, including the luminosity functions in different bands and the cross correlation with star-forming galaxies. The main thing I want to talk about are these emerging puzzles of a more vibrant early universe. And we have heard about this in previous talks on Monday and Tuesday, that we're seeing too many bright galaxies and some overly massive galaxies across redshift with JWST. And these are not what we anticipated in classical galaxy formation models calibrated at low redshift. And I should mention that there are many other evidences that are pointing to the same direction, probably not as significant as those two. We're seeing 2 early quenched galaxies, massive protoclusters, large number of dusty star-forming galaxies, early morphologically mature galaxies, DC galaxies, and accreting supermassive black holes, really massive quasars, and many more. So they're all suggesting that the structure formations seem to proceed more rapidly only at early times. And there are many solutions that has been explored in literature. Many of them revolve around modifying the galaxy formation model so that we can produce phenomena like bursty star formation, enhance the star formation efficiency in certain regimes, or top-heavy stellar initial mass function that could help reconcile many of these tensions. Well, another direction that you can go is to tweak the cosmology. So if you modify cosmology a little bit, this would systematically affect how structure formation proceeds. So halos build up earlier, so everything shows up earlier. And one way to do this, and one simple way to do this, is to change the initial condition of the universe. So this is the linear matter power spectrum. The power of fluctuations as a function of the scale of the fluctuations. And these observational data points are constrained from CMB and Lemma alpha forest. So here the punchline is that these constraints all truncate at fairly large scales. So we actually have very limited knowledge about the initial condition of the universe at subgalactic scales, where a lot of interesting features could live there. And this was a plot taken from a conference in 2022. And historically, there are a lot of interesting models that would suppress the small-scale power spectrum. And I would say that's motivated by the many old cosmological tensions which are now all gone. And in fact, there are equally interesting flavor of models that could enhance the small-scale power. And high-D galaxies, the abundance of high-D galaxies are actually providing a new window of constraining the initial condition of the universe at this scale. There's one model that I want to show as an example. It's called early dark energy. This is a model that was proposed to solve the Hubble tension. And this is a component that exists before recombination that accelerated the expansion of the universe by that time. It changed the size of the sound horizon. So if you redo the analysis of the CMB data, you would get a different Hubble constant. And we are among the first to realize that there's a side effect of this model that would systematically enhance the small-scale power spectrum gently, only by like 10 to 20%. This yellow line here is an example. It's a model. If you redo the analysis of CMB plus BAO data, assuming the existence of this component, and you get a Hubble constant around 73 that is fully consistent with local measurements. And this boosts the small-scale power, accelerates structure formation. So how do we tell the difference? How do we break the degeneracy of these possible explanations? One way to do this is through clustering. And this was mentioned already in Steve's talk. Here's a plot that I take from Julian Monod's paper, where he compares two scenarios that reproduce the UV luminosity function that gives rise to very different clustering power. Another thing that's specifically for early dark energy is that it leaves some imprints even on the large-scale distribution. It modifies the sound horizon, so you would see some difference in the amplitude of the location of the BAO feature. And these are some analytical predictions that we make at Redshift 2 that Roman could hopefully detect the difference between the two models. So far, everything are based on like very simple analytical predictions. But with Lumina, we can explicitly investigate all these phenomena. So I said that the fiducial Lumina simulation with lambda CDM cosmology is now evolved to Redshift 3. That's this left one. And we got lucky to have the computing time to do an early dark energy analog with exactly the same setup, physics resolution. And you can already see that the large-scale dark matter distribution already looks quite different at already Redshift 10, where structures emerge earlier in the early dark energy case. And we can also explicitly measure the clustering of galaxies in simulation. So here I construct this 3 scenario that would produce almost the same UV luminosity function consistent with JWST observations. One features a systematic UV luminosity boost. One features a large scatter of UV luminosity from bursty star formation. One is out-of-the-box prediction from the early dark energy raw. So it seems that the one with bursty star formation would produce lower clustering compared to the other 2. This is another aspect, another way of quantifying the bias of galaxies through cosmic variance. And Steve talked about beating cosmic variance earlier on Monday, but here we can actually leverage the cosmic variance and use that to probe the bias of these host halos of these bright galaxies we're seeing. So this is a project led by an undergrad student, Jia Hui, from Caltech, and now doing summer research at Harvard. So we look at a field of view. We look at the cosmic variance of bright galaxies in a single JWST pointing at Redshift 10 and compare that to what the panoramic survey is measuring, and you can see that it starts to is seemingly disfavoring the model with a large burstiness of the star formation. But I should say the error bars here are probably severely underestimated, so we really need Roman to provide more robust constraints. And the very last point I want to mention is that Lumina, the early dark energy version, is also radiation hydro simulation, so reionization is still modeled on the fly. We calibrate the 2 wrong, so they end the hydrogen reionization at around Redshift 5.5, consistent with observations, but they produce very different early reionization history. So you can see by Redshift 10, there are already larger islands of ionized gas developed in the early dark energy case. This would affect many things, like the number of Lambda alpha emitters that you can pick out at the extremely high redshift. I leave my concluding slide here, and happy to take questions. Okay.
We have time for a couple of questions. I have one right here.
At what redshift do you turn on your early dark energy?
So this is a component that's only active at redshift a few thousand, and then would decay and become basically negligible at lower redshift. So the way we implemented it is just simply change the initial condition plus a few other cosmological parameters. So there is no live component that we have to add in the simulation.
So you delay recombination.
By redshift, recombination still happens at the same time. It's just the sound horizon that you integrate over time becomes different.
Okay. Other questions? Lee?
I had a question about the Aegean demographics. That was your paper that you were referencing, right?
Yeah.
How are you predicting the number of completely dust enshrouded Aegean, which dominated higher redshift? Are you folding in dust into the modeling as well?
So for the ones that we call a normal Aegean, they have dust, and we basically take the column density distribution measured from X-ray surveys, and then assume a certain dust to matter ratio and convert that to the dust. For little red dots, it's purely empirical. We take the stack of the LRD SEDs, but acknowledge the uncertainties in IR, and use that to compute empirical bolometric corrections for the little red dots. And this is agnostic on how the SED of little red dots is produced.
Yeah, I'm not just worried about little red dots.
Mm-hmm.
The common thick Aegean issue has been around way before people mentioned little red dots.
Yeah. So we explored a little bit. So we tried a model with a very aggressively high compensate Aegean. That doesn't seem to affect the predictions a lot, probably only in the X-ray. But still, the data at the moment are not able to distinguish a normal compensate fraction versus extremely high one.
Okay. Question right here.
Just so what are LRDs in your model? And would you say that like this now settles what they are?
So the assumption we make is every single black hole with a mass below 10 to the 7 solar mass spends 30% of their time in little red dot phase. Well, population level of variables. Like we still don't know what's the detailed structure around little red dots that give rise to all the spectral features. And what's the seeding mechanism? Because the seeding mechanism in these simulations are very simple. You reach a certain halo mass threshold, you get a black hole seed there. But in reality, how you reach that reference point is unclear.
Okay. Let's give a final round of applause. I want to thank all the speakers for this session. This has been great, and all the speakers for the conference. This has been really just enlightening.